Hello everyone, I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about a light emitting diode, its construction and working. So let us see the brief outline of this topic. First we are going to see the introduction for LED and then discuss the construction, how an LED is made. And then the working principle of LED and the type of materials that are used for making LEDs, and finally the advantages and disadvantages of LED along with applications. So what is a light emitting diode? So a light emitting diode is a special kind of PN junction diode. We have already discussed in detail about the PN junction diode, and for the knowledge of PN junction diode you can refer to the previous lectures. And now in this lecture we are going to see how a PN junction diode is made in a special way to act as a light emitting diode. So in a light emitting diode, what happens is it is specially doped and made a different type of semiconductor so that this diode can emit light when it is forward biased. So we have also seen what a forward bias condition is. So when the diode, a PN junction diode, is specially doped, we are going to discuss what type of doping we are using and what type of materials that can be used. And when this PN junction diode, which is specially doped, is connected in forward bias, it will act as a light emitting diode. So now to make LEDs, what type of materials we use? To understand that, first we will discuss about different types of semiconductors. First one is the elemental semiconductors. What are elemental semiconductors? They are those elements which itself act as a semiconductor by origin. For example, we have silicon and germanium. When we take silicon and germanium, they behave like semiconductors. Semiconductors are those materials which are partly conducting. I can say they are pure semiconductors. Then comes the compound semiconductors. What are compound semiconductors? These semiconductors are formed by substances artificially. We are going to mix two different types of elements and we are going to get a compound, and we call it as a compound semiconductor. So example for a compound semiconductor is gallium arsenide. So we are going to mix these two elements, gallium and arsenide, and we are going to get a compound semiconductor. Now, most compound semiconductors are from combinations of elements from the third group and the fifth group of the periodic table. So, if you see the periodic table, you can see the periodic table here. This is how we are showing the periodic table. The few elements from the second, third, fourth, fifth and sixth group. Now, if you are talking about the third group elements and the fifth group elements. So, the third group elements are here we have taken boron, aluminium, gallium and indium. They can be mixed with nitrogen, phosphorus, arsenic and antimony. So, we can get gallium arsenide. When we mix gallium with arsenic, we may get gallium arsenide. So, one from third group and one for fifth group. And again gallium phosphide. We can also mix the gallium with phosphide. So, gallium mixed with a fifth group element phosphide, and then indium phosphide. Indium is from the third group, again phosphide from the fifth group. So, like this, when we are mixing different elements of different groups, for example, here we can take the third group and the fifth group, we are getting a compound semiconductor. Then we can also mix elements from second group and fifth group. So from the second group we have zinc and cadmium, and in the sixth we have seen selenium and tellurium. So second and sixth. So how is cadmium tellurium formed? Cadmium from the second group is combined with tellurium of the sixth group. So we are getting this compound semiconductor. And the same way zinc selenium. So zinc is from the second group and selenium from the sixth group. So we are getting this compound semiconductor. So we have given here, if you are taking a simple semiconductor, they are pures like silicon and germanium. And we are also calling them as elemental semiconductors. They are elemental semiconductor. And now when it comes to compound semiconductor, we are going to mix different elements. So we have seen the example of third and fifth, gallium arsenide, indium phosphide and gallium nitride. We have also seen second and sixth, that is zinc sulfide and zinc selenium. Also, we can mix two fourth group elements. So let us see the examples for mixing within the same group, that is fourth group element. So now when we have this fourth group element, we have carbon, silicon, germanium and strontium. So we can mix silicon and carbon. So we have silicon carbide. So these are a few examples of how compound semiconductors are made. Because when we have seen the definition for LED, it is a PN junction diode which is specially doped. Doping is nothing but the addition of an impurity or mixing up of two different elements. So here, most of the times for LEDs, we are using compound semiconductors. So light emitting diode, the examples if you take aluminium, indium, gallium phosphide, it is denoted by AlInGAP, and indium gallium nitride, so InGAN. This is the symbols we are using to show the compound semiconductors, and these are the two mostly common used semiconductors for LEDs. Wherever we are going to use LED technology, so we will be using LED made up of these type of materials, which are made up of compound semiconductors. So now coming to the symbol for LED. What is the symbol? So whenever we are drawing a circuit and if we have to denote an LED, we use a symbol to denote the LED. So here, this is the symbol for LED. What we have here is a triangle and with a vertical line. So this side denotes anode, positive, and this side denotes the cathode. And there are also two lines that are coming out, denoted or pointing outward. These arrows that are pointing outward always denotes the emission of light. Light being emitted. So these arrows are denoting the light emission. So we are calling it as LED. Light emitting diode. Now if you see a normal PN junction diode, the symbol for a normal PN junction diode is this. A triangle with a vertical line. This side is the positive, negative, or this is connected to the anode and this is connected to the cathode. So what is the difference here in the symbol for an LED is these two arrows which are pointing outward. That is also, the direction of the arrows is also very important. So this we call it as LED. And the two terminals we have are the anode and the cathode. That is how we are connecting them. Now coming to the working principle, how an LED works. What is the basic principle on which a light emitting diode works? So it is always operated under forward bias. So what is forward bias? When we are taking a light emitting diode, this is the symbol we are using. Light emitting diode with two arrows pointing outward, and when the P side is connected to the positive of the external supply and the N side is connected to the negative of the external supply, this we call it as forward bias. This is called as forward bias. This is positive of the external supply and this is negative of the external supply. So the P side is connected to positive and the N side is connected to negative. So a PN junction diode which is operated under forward bias, it gives rise to injection luminescence. So what is this luminescence? It is nothing but emission of radiation from a solid when it is supplied with some form of energy. So when we are giving some energy to the solid, then it will emit radiation, and that we are calling it as luminescence. So in LED we are going to see that light is being emitted. How it is emitted, we are going to understand. So whenever we are giving an energy input to a luminescent material, the final stage in the process is an electronic transition. What is an electronic transition? The movement of electrons from one level to another level. So for example, suppose we consider here two energy levels, E1, maybe I call it as ground state, whose energy is less than E2. E2 is higher energy level. Sometimes this E1 we also call it as ground state, and E2 we call it as excited state if there are only two states. Now, what we are seeing here is whenever there is a transition between two energy levels, E2 and E1, and as told, E2 is more than E1. The energy of this level is higher than that of E1. Now, whenever there is a transition from E2 to E1, that is from higher energy level to lower energy level, there is a transition. Then energy is being emitted. So this emission of radiation or energy, we can calculate its wavelength using our basic formula which was given by Planck. What was Planck's formula? E is equal to h nu. Or I can also write it in terms of lambda as hc by lambda. So if I have to get lambda, lambda will be equal to hc upon E. If I have to calculate the wavelength, and this energy emitted is nothing but the difference between the two energy levels. So I can simply write it as hc upon E2 minus E1, or this is nothing but the difference in energy, we write it as Eg. So lambda, the wavelength of the emitted radiation, can be calculated using lambda is equal to hc upon Eg. H is nothing but the Planck's constant here, which is given by Planck, whose value is 6.625 into 10 power minus 34 joules second. And c is the velocity of light. Its value is also constant, 3 into 10 power 8 meters per second. So now h and c both are constants. So the wavelength of the radiation that is emitted depends upon the difference in energy levels. What is Eg here? Eg is nothing but E2 minus E1. So the wavelength can be calculated using this formula, and Eg is nothing but E2 minus E1. Now whenever we are talking about this transition, E1 and E2 may not be single energy levels. There is a possibility that there may be groups of energy levels. So when emission takes place, instead of a single wavelength, a band of wavelength is also emitted. So whenever we are talking about light, it may not be a single wavelength, because I may take the energy levels of E1 very close. They are a group of energy levels, and E2 are also a group of energy levels. So whenever there is a transition from here to here or from here to here, there is a slight difference in wavelength. So a band of wavelength is emitted. So a group of wavelengths put together, we are calling it as a band of wavelength. Now coming to the construction of LED. How an LED is constructed. So LED is constructed using diffusion method. When we have discussed about the formation of a PN junction diode, we have seen different methods, and in that we have discussed very clearly about the diffusion process. Diffusion is always a process in which the atoms from the higher concentration side will move on to the lower concentration. So here what we are using is the diffusion method. A p-type impurity is painted on an n-type and both are heated. So now if you see the figure here, so we have a p-type and n-type. This is the diffused p-type and you have the n-type. So on the n-type, we will keep a p-type material and then heat it to a very high temperature. Then what happens? Impurities of the n-type and impurities of the p-type will diffuse into n-type and they will form a p-n junction. And also we have to see that LED has to be designed and constructed in such a way that most of the radiative recombinations takes place from the side that is nearest to the surface. So whenever there is recombination of charge carriers, so you can see here the recombination happening, it should be always very nearer to the surface. That will help in minimizing the loss of energy due to reabsorption. Now also we need to see that the p-n junction layer has to be parallel and closer to the surface layer. Whatever junction that is formed, it has to be always parallel to the surface. And electrical contacts are made leaving as much of the upper surface of the material uncovered. So we are going to have electrical contacts, metallized electrical contacts. So this is a metal film we are putting for connection. And at the bottom also we have a metal film. Okay. So these metal films are used to have the contacts to the anode and the cathode. And a part of it is left uncovered. Why we are doing it is uncovered? Because when the recombination takes place and the radiation is generated between p and n layers, the radiation escapes through the top layer. So we are going to leave a space for the light emission. This is how the radiation is going to come out from the top surface whenever there is recombination. So we are going to see the function. So when we are constructing itself, it has to be kept in mind that the top surface of the layer of the p-n junction cannot be covered completely. It should be, most of it is left open so that the radiation can come out. But the bottom layer or the bottom electrode, a reflective layer is added to improve the efficiency. So if the LED has to have a high efficiency, what we do is we will put a reflective layer so that most of the light is reflected. Now we have already discussed that we are taking this LED and connecting it in forward bias. So what happens when a forward current is given to the p-n junction? Okay, so when we are giving a forward current means P is connected to the positive and N is connected to the negative. So why we have to give this forward bias also we have discussed, because whenever we are having a P and N junctions, P type semiconductor is having majority carriers are holes, and in N type the majority carriers are electrons. And because of the diffusion, when they are brought together, electrons from the N side will diffuse onto the P side and holes from the P side will diffuse onto the N side. And this diffusion process will leave positive ions, immobile ions on the N side and negative immobile ions on the P side, and because of which there is a depletion layer that is formed, which acts as a potential barrier. So in order to overcome this potential barrier, we do the biasing. And here in forward biasing, what happens is, because when we are doing the forward bias, the holes in the P-type region will move on to the N side. Otherwise, without the bias, what is happening? Because of the barrier, the movement of electrons and holes from the N side and the P side is stopped. So because of the forward current, what is happening now? The holes will move. So if you see the figure here down, what is happening? The holes are moving from the P side to the N side, and you have the electrons that are moving from the N side to the P side. Means they gain sufficient energy because of the forward current. The holes in the P-type region move to the N-type region, and the electrons in the N-type region will move on to the P side. So under forward bias, majority carriers from both the junctions, both the sides of the junction cross the barrier and enter the other side where there are minority carriers. So what are minority and what are majority? So when I said holes are the majority here, electrons are minority. Electrons are minority charge carriers. And in N-type, when I say electrons are the majority carriers, holes are minority. Holes are minority carriers. Now, when we see the movement of electrons from the N side to the P side, means whatever is in minority here, that is being injected onto the P side. So the electrons which are in minority on the P side are being injected. So we call it as minority carrier injection. The same way on to the N side, holes are being injected. So there is movement of holes. So this we call it as minority carrier injection. Now these excess minority carriers, while diffusing away from the junction, they undergo radiative recombination. So two terms you need to understand here. The first one is diffusion. Diffusion is the movement of the charge carriers of higher concentration to lower concentration. Now when these charges, the excess minority carriers, while they diffuse away from the junction, they undergo radiative recombination with the majority carriers. So the minority carriers, if they are holes, they will recombine with the electrons, and the minority carriers on the P side, on the N side, which are holes, they also will recombine with the electrons. So in positive or in forward bias, there is radiative recombination. But when it is connected in reverse bias, there is no carrier injection. And so there is no light that is emitted. So what happens when these injected carriers recombine? When there is recombination of these electrons and holes, the energy difference before and after recombination is released as light. So whenever there is recombination of electrons with the holes, then what happens? The difference in energy is being emitted as light. So this emitted light depends upon the energy gap. What is the energy that is emitted is E2 minus E1, and this depends upon the energy gap, Eg of the compound semiconductor, that is the material we are using. And conventional silicon diodes do not emit light because the recombination energy becomes thermal energy. So you should get a doubt why we are not using the elemental semiconductors as LEDs and why do we go for a compound semiconductor. So if we are going for a pure silicon or for elemental semiconductors like silicon, they do not emit light because during recombination, whatever energy that is emitted, it is emitted in the form of heat and we don't get light. So whenever we make LEDs, we use compound semiconductors. So let us understand the phenomena or the working of the LED with the help of this diagram. So what we have seen here is a P-type and N-type materials are doped. We have taken different elements from different groups and combined so that a junction is formed. So once a junction is formed, there is diffusion of electrons from N side to P side and holes from P side onto N side. So when this diffusion happens, there are immobile ions that are developed on the either side of the junction. Negative ions on the P side and positive ions on the N side. And because of which there is a depletion layer that is formed. And the depletion layer will be free of the charges, and because of these positive and negative ions, there is a potential barrier that is formed. And because of this potential barrier to overcome, what we do is we connect a bias. We are connecting an external voltage source, positive and negative. So when this external voltage source is connected, the holes will be pushed across the junction and the electrons also will get energy to get pushed across the junction or to overcome the barrier. So while diffusing away, what happens is there is recombination. So the recombination of free electrons and holes takes place near the junction. So all this are denoting the recombination of electrons and holes. So whenever there is recombination of electrons and holes, the difference in energy is being emitted as light. So this is how an LED functions. So when you see semiconductor diodes, they produce radiation when electrons from the conduction band recombine with the holes in the valence band, and the emitted radiation is absorbed by the semiconducting material. So whenever we are talking about a conduction band and valence band, so here this is the valence band and this is the conduction band. Conduction band means it denotes the energies of all the conduction electrons, that is, which are free electrons. And the valence band denotes the energies of all the valence electrons. Now, whenever an electron from the conduction band jumps into the valence band, the difference in energy is being emitted, but it is absorbed by the surrounding semiconductor material. But in case of an LED, what happens? The semiconductor has a high energy gap and the junction is constructed in such a way that the radiation can escape from the junction. So if you see the diagram here, P side, N side, it is connected to an external supply in forward bias. There is flow of electrons from N to P and there will be flow of holes from P to N. And there are radiative recombinations that are happening at the junction, and because of which the radiations are emitted. It is given out in the form of photons and can be emitted across the junction. So now when it comes to the efficiency, the internal quantum efficiency of LED materials can approach to 100% because the external efficiencies are much lower. So we expect 100%, but if you see the actual efficiencies, they are much lower. What is the reason for this is, most of the emitted radiation strikes the material at angles greater than the critical angle. And so it is lost due to total internal reflection. So here we need to understand what is total internal reflection. So what is total internal reflection? Whenever a light ray is incident at an angle greater than the critical angle, what happens is the light ray gets reflected back into the same medium. So what is the condition here? It should come from a denser medium to a rarer medium, and the angle of incidence should be greater than critical angle. So whenever the light is incident or it is striking the material interface at an angle greater than the critical angle, so it comes back and it is lost due to total internal reflection. Now we are using here most of the time third and fifth group. We have already discussed in elemental semiconductors. So a combination, we have taken a general combination is from third and fourth group, and they have high refractive indices. So their critical angles are very small. So the critical angle for a given elemental semiconductor is very small. Then what happens? What happens here is there is loss of light due to total internal reflection. We are taking the example of gallium phosphide and air interface. We have taken the we have taken a compound semiconductor, gallium phosphide. So at the air interface, this material and air interface, what happens? The critical angle is 17. Means the rays that are incident at an angle greater than this 17 degrees are lost. So what we have to do whenever we are taking this material, we have to see that light rays are incident at the interface at an angle less than 17 degrees. Otherwise, it would be lost. So now to improve this situation, there are two ways. There are two ways to take care of this situation so that the loss of light can be minimized. So what is the first one is to ensure that the rays strike at an angle less than the critical angle. So for gallium phosphide, we have seen that the critical angle is 17 degree. So we take care that the rays that are incident at the interface will be incident at an angle less than 17 degree. So how do we ensure that is by shaping the semiconductor surface into a hemisphere. If you see the diagram here, we have seen that it is formed by diffusion. So when the p-n junction is formed, this is n-type substrate and this is p-type, and this we are trying to make it in the form of a hemisphere. So what will happen here if it is made in the form of a hemisphere? The angle that which it strikes will be less than 17. So the radiation then strikes the semiconductor air surface at an angle less than the critical angle and hence not lost. But this technique is too difficult, no, to make this hemispherical shape and see or ensure that it is incident at an angle less than 17 degree is difficult, and also it's an expensive process because we'll have to shape them. So what is the second solution for it? The second technique is to encapsulate the junction in a transparent plastic medium of high refractive index. So what we do is, if this is the p-n junction, we will keep it enclosed in a plastic mold. This is the plastic mold, which is again having the shape of a hemisphere. By molding the plastic into a hemispherical shape, loss of light or radiation at the interface can be minimized. So now in a typical light emitting diode, what we see here is when there is no voltage that is applied, there is no movement of charges. But when an external voltage is applied, what happens is the movement of holes from P to the N and movement of electrons from N to P, and when they recombine, the recombination of electrons and holes gives rise to light. So this is how we are showing the light that is emitted. Now coming to the formula that we are going to use, or the current voltage relationship for a LED is given by I is equal to I naught exponential EV by beta KT minus 1. So this is the formula we are going to use to calculate the current or the voltage that has to be applied. So I is the current and I naught here denotes the saturation current. I naught is the saturation current. E is the charge of the electron. E is the charge of electron. Its value is given by 1.6 into 10 power minus 19 coulombs. And V is the applied voltage. We are connecting it in forward bias and we are applying the voltage. So V is the applied voltage. And beta is the material constant. And its value will vary between 1 and 2. Depending upon the temperature and the semiconductor material we are using. So beta is the material constant. K here is again the Boltzmann constant. K is also a constant given by Boltzmann. So it is Boltzmann constant. Its value is 1.38 into 10 power minus 23 joules per Kelvin. And T is the temperature. So definitely it depends upon the temperature of the semiconductor also. So I can be calculated using the formula I naught exponential EV by beta KT minus 1. So no, beta is a constant depending upon the material. K is the Boltzmann constant. E is also a constant. So it varies with temperature and the applied voltage. Now, when we see these light emitting diodes, they are heavily doped. We can see there are special type of PN junction diodes that are heavily doped. We have seen, and depending upon the material that we are using, LEDs will emit light in different colors, because whenever we see these LEDs in market, they are available in different colors. So how are these colors emitted, or in a given spectral wavelength, how these colors are produced? So that is what we are going to discuss now. So the color of an LED is determined by the material that is used. So it depends. The color is related to the wavelength. So if the wavelength varies, the color varies. So the LED, the light that is emitted by an LED may be in different colors, and it depends upon the material we are using. Then the two type of materials that are used in LEDs are aluminium gallium indium phosphide and indium gallium nitride alloys. So these are the two type of materials which are extensively used in making the LEDs. So in aluminium alloys, we get yellow, orange and red. So when this type of materials are used, when these alloys are used, you get the yellow, orange and the red light. And when indium alloys are used, we are getting the blue, green and white light. And slight changes in the composition of these materials may change the color. You may get a slightly different color when the composition varies. So here we can see the different colors also. What is the type of material we are using, what wavelength and what color, at what voltage. So this puts everything in a nutshell. So when the type of material used is gallium arsenide, the wavelength that is emitted is in the range 850 to 940 nanometer and it is in the infrared region, and the voltage is 1.2 volt. Now when it comes to the visible region, that is from red to blue. If you see, all this is the visible region. So we are using gallium arsenic phosphide. The range is 630 to 660 nanometer. It is in the red range and 1.8 volt. So when the type of material that we are using is varying, the wavelengths that are emitted differs. So when the wavelength varies, the color of the light that is emitted also varies. That is how we see different color LEDs in the market. Now coming to the materials. So whenever we are choosing the materials, the main requirement for suitable LED materials are they should have an appropriate energy gap. So the energy gaps which are greater than or equal to 2 electron volt are required to get visible radiation. So whenever we need a visible radiation, the energy gap has to be greater than or equal to 2 electron volt. And both P and N type must exist at low resistivity. The resistivities have to be very low. So they will have efficient radiative pathways, so that the pathway for the radiation also will be very efficient. And what are the advantages? Coming to the advantages. So most of the times we use LEDs in electronic displays. So what are the advantages of having an LED in an electronic display? So the output is bright and the intensity can be controlled by varying the current. So the intensity of the radiation can be controlled with the help of the current, and they can also be operated over a wide range of temperature, that is 0 to 70 degree Celsius, a wide range of temperature. And then very fast response time. And the response time, it is in the order of nanoseconds. Nanosecond means 10 power minus 9 seconds. You can imagine how small it is. The response time is in the order of 10 power minus 9 seconds. And so it's a very useful source for optical communication. And the other advantage is it is available in different colors also. And then the next advantage is they are very small in size and so can be closely packed for a high density display. So we can pack them very close because of smaller size. And long life. So the life is about 10 power 5 hours. So about 10 lakh hours. And high degree reliability. The reliability is also high. And the viewing angle is not limited. You can view it at any angle. And very rugged and hence suitable for any type of environment. So it does not get affected by the environment, or it can withstand high temperatures and any weather. So we call it as rugged and suitable for any kind of environment. So any doubts or any clarification you need regarding this topic, you can refer to the book Semiconductor Devices, Physics and Technology by Simon Z. and Ming Li. Most of the topics are covered in this book. You can refer to this book and get your doubts clarified. Thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.